Hello and welcome to Team 1095's presentation. Between myself, Ethan, and Laith, we completed Problem B for the SIMIODE 2020 competition. Let's get started.
The apparatus we created to model the bird's path as it traveled around the wheel consisted of a wheel with radius r, denoted in blue, an object with mass m, denoted as the green cube. The object is then attached to a wheel by a distance h, shown in orange. The motion of the wheel, for our example, will be clockwise. Our assumptions for this model. Assumption 1. Any movement of the object in either direction from the topmost position of the wheel will result in the wheel turning in that direction and starting angular velocity. This doesn't necessarily mean that the object moves out of position, but can shift its weight, changing the direction of the downward force it's exerting on the wheel and starting the clockwise or counterclockwise motion. Assumption 2. The object and wheel will move at the same time, though the object will have to change motion in such a way to accelerate the velocity of the wheel as it's attached to it while rotating. This will be centripetal force, like a figure skater bringing in their arms to increase spin speed. Assumption 3. While not an ideal initial point for full rotation, the object can be at the bottom of the wheel and sway in a pendulum-like motion until successfully completing a rotation. The equations and variables used in our model are as follows. Force equals mass times acceleration. Torque, tau, equals radius times force times sine of theta. Note that the derivative of angular momentum is torque. The moment of inertia, I, equals mass times radius squared. Angular momentum, L, equals the moment of inertia, I, times omega. Angular velocity, omega theta prime, equals delta theta, the change in angle over time, divided by delta t, the change in time. Angular acceleration equals the change in omega, omega final minus omega, divided by delta t, the change in time. The building of our model. Considering that force equals mass times acceleration, and acceleration in our model's case is the downward force of gravity, we have force equals mass times gravity. The rotational force applied to the wheel is torque, since the object is attached to the wheel, and that is expressed as torque equals radius times force times sine of the angle theta. The radius will include the distance between the center of the wheel and the outer edge of the wheel, and will include the distance h, which can be modeled as a function of theta. Since the distance h can move freely, with substitution, this yields torque equals r plus h of theta times mass times gravity, or force, times sine of the angle theta. Note that r plus h of theta and r naught plus h refer to the same length. Torque is also described as the derivative of angular momentum L. Even without knowing the velocity and time displacement of the wheel and object respectively, we can still express torque as T equals d dt L. Since angular momentum is the moment of inertia times angular velocity, or rotational rate, then we can rewrite this equation as tau equals d dt I omega. Per the product rule, we get tau equals di dt omega plus d omega dt I. For di dt, as there are two objects in this apparatus, we need the inertia for both, creating I total equals I wheel plus I object. If we ignore the mass of the wheel for now, we get I total equals I wheel plus m times r plus h of theta squared. If we consider angular velocity as just a variable, omega equals theta prime, then altogether we have di dt omega equals I wheel plus m times r plus h of theta squared times theta prime.
Bringing over the equation from the previous slide, we just expanded it with some distribution and simplification. We rewrote a couple variables, and we were left with the equation you see in red. We also didn't want to forget the total distance between the center of the wheel and the object, so we rewrote r to be r naught plus h. And since we already had an equation for the total inertia of the system, and we knew that the derivative of omega could be written as theta double prime, we ended up with the equation you see in blue. So here we have our equation in blue at the top. To rid the variable tau, we replaced it with the original equation for torque, and then we also replaced h prime with dh over d theta times d theta over dt, and d theta over dt is just theta prime, and that left us with the equation in red. Then we solved for theta double prime, and that left us with the equation at the bottom, and for easier reference, the equation in green. And just to conclude the building of our model, what you see in blue are the constants. G sine of theta in green accounts for when torque and acceleration are at its max, and the expression that you see in orange accounts for the ice skater effect, where h will compress with respect to theta and increase the acceleration.
Okay, so what if we start from the bottom as an initial condition? So if the object starts from the bottom and we understand the initial position at theta equals to 0, theta is actually equal to 270 if you go by the quadrants, but our convention is we're going to make it theta equal to 0. That's our convention. There will be, of course, no velocity and no acceleration. However, as the object can move freely while attached to the wheel, it can shift its weight, changing the direction of the torque applied on the wheel. As an example, if that shift happens forward, counterclockwise, as you would see in image A, the gravity will start applying a downward acceleration to push the object in the opposite direction, as you see in image B. This when the compression of H can occur, which will increase the object acceleration clockwise again. Repetition of this action will lead to breaching theta equals to 90 counterclockwise, where H can be fully decompressed and allowing the maximum torque and acceleration that can be applied and should yield a total revolution, where the previously mentioned model can be reapplied. As the angular velocity changes, the H value can compress or decompresses to create as much acceleration as possible. To account for this, we include h of sine of theta in our model. The h value could be constant, which would indicate no motion from the object occurs, though there be no higher values of acceleration compared to what there would be if h were to compress. With compression, the object moves up and down with respect to outer surface of the wheel, and at an ideal condition, maximum velocity will occur around the bottom of the wheel, theta equals to 180 from initial theta, since gravity would start exerting on the downward force on the object, effectively decelerating it and slowing the velocity h, would then decompresses and it prepare for another revolution as it reaches theta point again. Maximum angular acceleration would occur around theta equals to 90 when torque is at its most and since gravity is working straight down on the object.
And finally, let's talk about the maximum speed of the wheel. If we substitute within our model slightly, we get the equation you see in blue, where we take h sine of theta and insert it into the model, and then we clear out any derivatives. Integration with dh over d theta times d theta over dt would not work, and solving for 0 yields imaginary numbers, so we can use initial conditions to find acceleration and then maximum velocity. Using initial conditions, we can leverage the model to solve for theta double prime. If we consider that distance equals velocity times time, and the angular version of that is theta equals theta prime times time, and theta prime equals theta double prime times time, then we can continually compute for theta prime by increasing time in intervals and making sure to add the previous conditions using the equations you see here in red, which will yield a new theta prime and theta, and thus tells us the maximum velocity and acceleration at a particular angle. And to wrap up, if we treat the initial position as theta equals 0 degrees at the top and the clockwise motion with positive angles, then torque will be at its greatest value at the right, around theta equals 90 degrees, since it's taking advantage of the most gravitational push and thus the greatest point of acceleration. At the bottom of the wheel, the velocity will be at its greatest since gravity would start to decelerate the object as the angle increases beyond theta equals 180 degrees, and the torque applied will be negative. This is true if h is constant or if h equals h sine of theta to account for compression for acceleration. And the last thing to consider here, air resistance can be taken into consideration with all motion previously mentioned, though since the object is not in projectile motion as it's attached to the wheel and density was not considered in the initial conditions, it was excluded. We can say, however, that given the number of variables to account for in the air resistance equation in blue, including density of the surrounding fluid, speed of the object relative to said fluid, the drag coefficient and the cross-sectional area of the object, we realized that our model could have become imprecise, or that if it did accurately account for air resistance, that it would have been negligible since the wheel was dependent on the object for motion. And here are the references that we used. Thank you for watching, and stay safe.